Log on, tune in, find out. Another good idea from Cambridge.
It's been a very long term with lots of talks, and we are sort of approaching the end. And we are very happy to have Wolfgang Wagner, who was a very constant visitor of this special semester here, and I'm sure has done a lot of very good work in the last 2 months, to give us a talk on kinetic equations and Markov jump processes. And then tomorrow is going to be one final seminar day with Maria de Mar Gonzalez and José Antonio Carrillo talking about some neuroscience and so forth. And then I think we had many talks this term. I don't know, I have to even start counting. Okay, please, thank you very much.
Yeah, thanks for the introduction. Actually, I really got the week with the lowest concentration of participants. But anyway, I will try to do my best here. Of course, I would like to thank the organizers for the invitation. It's always a pleasure to be in Cambridge, in particular at the Newton Institute. So my talk is about kinetic equations and Markov jump processes. This is a very general topic. Originally, I had planned to talk about what is now the second part of the talk, namely a specific phase transition which occurs in fragmentation models. But then I decided that this would be too specific, so I will start with an extended introduction into the subject, so in order to put the fragmentation models into a certain context. And of course, not everybody is familiar with each of the specific topics which are covered by this semester. So the kinetic equations which will be considered are here. And in terms of the underlying jump dynamics, they can be characterized as follows. So in the Boltzmann equation, the jump mechanism is based on a transformation of 2 particles into 2 particles. This means a collision, so a change of velocity. In the Smoluchowski equation, the basic transformation is 2 particles give 1 particle. Simply they stick together, form a bigger one. In the fragmentation equation, the basic jump consists in splitting of 1 particle. 1 particle splits into many. So in the first case, you have a constant number of particles. In the second case, the number of particles goes down, and in the last case, the number of particles goes up. And of course, in each of the single jump events, there's mass conservation. And according to the basic jump mechanism, the first 2 equations are nonlinear, and the last one is linear. So linear might look rather trivial, but it turns out that even if it is linear, it has some interesting. Can we remove this? Yeah, you can try. Even so, it's linear. It has some interesting properties. Roughly speaking, it can happen that these individual jumps of splitting 1 particle go very fast, so fast that in a finite amount of time, particles of 0 size occur. Of course, there must be very many of them, so they form a non-trivial part of the whole system. And this is the phase transition which will be discussed in the second part. So this is in short the short story of the whole talk. Now we will go through it step by step. Here's the spatially homogeneous Boltzmann equation. which describes the time evolution of a certain number density. And the number density tells us how many or which percentage of the molecules are in a given range of the velocity space. The equation itself is rather simple. It becomes difficult due to this transformation which enters the solution here. And this is one of the possible representations of the two conservation laws, namely conservation of momentum and energy. So if you want to model a collision of two particles having a velocity before and after collision, and you want to keep momentum and energy fixed, you have 6 degrees of freedom of the outcome and 4 conservation laws which you have to obey. This means you have 2 degrees of freedom left, and this is one of the possible representations. Here are the 2 degrees of freedom given as an element of the unit sphere in R3. Another form of the Boltzmann equation is the weak form. So if you multiply with the test function phi and then integrate over the whole velocity space, you end up with this form. And the weak forms are, at least for me, they are more intuitively clear than the original equations, because on the right-hand side you see the kind of nonlinearity, it means binary interaction, and inside the brackets you see what happens during a single interaction. Namely, two particles with two velocities change their velocities into the star values. Now the corresponding particle system simply contains of a certain number n of particles. Each particle is characterized by its velocity, and the interaction or the jump mechanism, if you want to put it in a more general perspective, is given by this transformation, where the V star and W star are defined here. Now the connection between the particle system, I should say the interaction of course involves some randomness. I did not talk about the interaction at all. So it involves a certain kind of randomness, namely at a given moment two elements of the particle system are chosen, I and j, and then a random element of the unit sphere is chosen, so that these new velocities can be calculated. And these probability laws are given by the last object, which has not been explained so far, namely by the Boltzmann collision kernel, which occurs in the equation. Now the connection between this particle system and the equation is given by the so-called chaos property. This type of result goes back to Markov, to a paper by Markov in 1956, and he formulated the following. Now let's Pn superscript n denote the density function, the distribution function of the whole particle system, and the sub k denotes the k marginal. Marginal is obtained if you integrate out the last n minus k variables. Then the statement is the following: if there is such a factorization property at time 0, then there will be such a factorization property at all later times, and the factor is just the solution of the Boltzmann equation. So originally Markov described this kind of property by saying, or this kind of result by saying that the Boltzmann property propagates in time. Having in mind Boltzmann property is this factorization, and propagation means once you have the property at time equals 0, you have it at all later times. Only a couple of years later, basically in papers by McKean, this type of result was then renamed by the term propagation of chaos. Now we step to Smoluchowski's correlation equation. This is an equation which first occurred in the literature in 1916. It describes also the time evolution of a certain number density. In this case, so to say, the state space of a single object is just the size, x. Here, the particular case of the discrete size is written down, which means that there is a certain minimal object called monomer, and then when time evolves, several monomers stick together, form bigger particles, and the solution C of t and x describes the relative amount of particles at a given interval of the size space, or in the discrete case, at a given size. In some sense, it's quite similar to the Boltzmann equation. You have a gain term with a positive sign and the loss term with a negative sign. But again, instead of explaining here the different terms in more detail, I prefer to have a look at the weak form. So again, you can multiply with the test function, integrate over the state space, which in this case means summing up over the discrete sizes. Then you obtain again something very similar to the Boltzmann equation. Here you have the product of the solution, which means there's a binary interaction, so two particles are involved. And inside the bracket, you see what happens to the particles, namely two particles of sizes x and y form a bigger one of the size x plus y. So the particle system is now, the particles in the system are now characterized by their size, the number of monomers which they contain, and the interaction is a simple plus operation. And of course, the random laws of the interaction are given by the kernel, which figures in the equation. Now, the difference to the Boltzmann equation is that here you have a variable number of particles. In the Boltzmann case, it was constant. Here it goes down. This makes it difficult to apply the type of the propagation of, or apply something like the chaos property. You know, if you have a variable number of variables, how do you want to really formulate in a precise way this factorization? Therefore, in this case, the connection between the particle system and the equation is made using so-called empirical measures, which means the following. Given the particle system, these are the particles, you simply you sum up delta measures concentrated in these particles, sum up over the system, normalize in an appropriate way. And of course, you have to normalize. I did not mention these technicalities before. You have to normalize in an appropriate way the jump frequencies. Then you can prove a theorem similar in some sense to what we had before in the Boltzmann case. Namely, you can prove propagation of convergence of empirical measures. Which means once you have convergence, these are random objects. Once they converge in the distributional sense to a deterministic object at time 0, then you will have this type of convergence at all later times, and the deterministic limit will just be the solution of Smoluchowski's correlation equation. Here's a slight misuse of notation, because in the discrete case, which was on the previous slide, of course you can skip just the D here. You just can make the statement for each single possible size. But of course this works in more general situations where you have continuous or mixed size spaces. And this machinery works very well in systems where you have a variable number of particles.
Excuse me.
Yep.
Does the initial number of particles scale with n somehow?
The initial number of particles you can imagine is just the small n.
Okay.
Yeah? So at the beginning you have to normalize it to somehow. So if you start with n particles and normalize it by n, then your initial stuff has just mass 1. Then the number changes and you get the statement. So now I move to fragmentation equation.
Sorry, I was too slow. Are there cases known where essentially you know initial data where you don't have the convergence of the empirical measure, but through the time evolution you enter a state where you would have the convergence?
Yeah, this is a good question. I do not know about such examples in finite time, but in infinite time this can happen. So you start with something which does not, but this is very far going, we're beyond the topic. You can start with something which does not converge, and then if you have a unique equilibrium, in equilibrium you can have this factorization property. But usually in finite time I don't think that it will work. Fragmentation. So this is the third kind of kinetic equation I want to consider here, and this is a type of equation for which I want to discuss these specific properties in the second part of the talk. So again, the solution C is a number density, and as in the Smoluchowski case, coagulation case, this is a number density on some size space. So the x is now just a scalar, and the solution tells you what is the relative amount of particles of objects of a given size x at time t. Similarity, of course, is in having a positive and a negative term here, which means gain and loss. And again, I prefer, before this, I will discuss this later a little bit, I look at the same time as a weak form, which can be explained in some sense easier than the above stuff. So in the weak form, you again multiply with a test function and look what happens. Now here the right hand side can be explained a little bit easier. Of course it's linear, so this is linear, this is linear. This means because the mechanism is considered to be such that all the particles behave independently and each particle has the possibility to split into pieces. So it's linear, and multiple fragmentation is considered. So the mechanism is described somehow by a kernel f, probability kernel f, which tells you what is the distribution of the cloud of fragments which comes out when a particle of size x splits into pieces. And here you see the fragments, and here you see that only just one particle is involved. Now the system is now again almost the same as in the previous case. And the jump is, as I explained before, particles move independently and each particle has the possibility to split into pieces. Now it's linear. So in the linear case, one really does not have to bother about convergence. It's simply enough to correctly define the stochastic particle system and then to take expectations. And this will be done via so-called Kolmogorov forward equation. Now, because this equation will be used later on, I will spend a couple of slides first on explaining the connection between the particle system and the weak form, so to say derive the weak form via the Kolmogorov equation, and then I will spend some minutes on explaining the connection between the weak form and the strong form, which I have not discussed so far. And the reason why I will do this is, the reason for the two steps are quite different. So I will explain this connection between the particle system and the weak form because it's much easier than in the previous two cases of Boltzmann and Smoluchowski equation, because we do not need convergence. We just have to justify taking the expectation, and the second step will be explained in some more detail because it's not so obvious as so the connection between the functions which occur here and the functions which occur here is not so obvious as it was in the previous two cases. So first, I will now discuss how the weak form of the equation is derived from the particle system. So here the time evolution of this specific Markov jump process is explained a little bit in more detail. So this is just a notation for all the particles. We have a variable number of particles, and each particle is just a scalar. The size has a size. Then all particles move independently. Each of them waits an exponentially distributed time until the next event or until the next splitting event. And the parameter of this waiting time is given by this function a, which was in the equations. And then at that random moment, okay, the next splitting moment, the xi, which is chosen again. Okay, if you start with the xi, then we just have this xi, and this is split into k pieces according to this kernel. Now the function a, which is called the fragmentation rate, is supposed to be bounded on the state space of a single particle, and the fragmentation kernel is supposed to be a probability for each x. It's a probability measure on this cloud, on this space of possible clouds of fragments. You see, for handling the multiple fragmentation case, you need quite a bit of good notations, just to not to get lost in all these possible events which can happen. Now, what is assumed is a reasonable mass conservation property, which simply means that with probability 1, the sum of all fragments just gives the original particle. Okay, this is a more detailed description of the process. Now, in order to do something, or in order to work with this object, it is more convenient, again, to move from the particle picture to the measure valued picture just by summing up the delta measures in the sizes where the particle is over the whole system. Here we do not need any normalization because it's just independent. We can just take the expectation at the end. So the state space of this process is are now all finite combinations of delta measures on the x. The jump kernel is just a mixture of these transformations This is a transformation in a more formal setting, which tells you, given a state xi, the jump consists in removing one particle and adding the fragments to the system. So the jump kernel, which tells us how often and how frequently all the different possibilities occurs, is obtained from this transformation, and then it is mixed first over all possible fragments and then is summed up over the system. Then simply the statement is that if you take, now your xi process is a measure-valued stuff, is a measure-valued process. If you take the expectation, then this expectation satisfies this equation, which is just the weak form of the fragmentation equation, which was on the first slide of this part of the talk. Now, I mean, okay, I promise that this can be simply derived from the Kolmogorov forward equation. So this is one of the possible forms, or one of the forms of the so-called Kolmogorov forward equation, which tells us that the derivative of the expectation of a certain functional of the process can be expressed via the expectation of another functional of the process. And this other functional is given here, which is the so-called generator of the process. And that's it. Now you have to remember what were the ingredients of the process we defined before. This was a jump kernel, which has to be plugged in here. And then if you take a specific test function, which is just, this is on the big space, on the measured space. You just take a test function of the single particle space and integrate it with respect to the argument. Just a formal description of just summing up the values of the small phi over the whole system. And you plug it in here, you end up with this equation. You can check it later. I mean, I think the transparencies will be on the net. So this was the first step. The derivation of the weak form of the equation from the particle system. Now I will explain the connection between the weak form and the strong form of the fragmentation equation. So this was the starting point, the weak form of the fragmentation equation, which we just derived. And now we first derive this property, which will be used later, and therefore it got even a symbol here, a name, a star, so I will use this property later in the talk several times, which allows us at the end to simplify or to transform this, in some sense, inconvenient part of the right-hand side of the equation. So what we are doing is the following. Given the f, so the f is the fragmentation kernel, which tells you what is the probability of various clouds of fragments to arrive. We restrict this to the k, to the x to the k, where k fragments are obtained, symmetrize it, just by summing up over all permutations. Then we take the one marginal by integrating out over the n minus or k minus 1 variables, and then we sum up these k1 marginals in this way. It's just a definition, a helpful definition. Having all this, so to say, prepared, we can transform this term, which occurs here on the right-hand side of the weak form of the fragmentation equation, the following way. So first we write the z as the sum or the union of the k powers of the x. And you see this object is symmetric, so the f can be replaced by the symmetrization. Then once it's symmetric, each of these terms gives the same. Just integrate with respect to the one marginal, multiply it by a factor of k, and then using that definition you end up with a much easier object, which is an integral with respect to the x. The x is a one-dimensional state space of a single particle. This was a complicated object here. Okay, now you don't have to remember anyway, you will not remember this star. So I reproduce the star formula in each of the slides where I will need it. So according to this property, we transform this first term on the right-hand side of the weak equation into that one. Just we use this property, plug it in, get this form. This form will be reproduced on the next transparency. This is blackboard is easier for such things, but I would not like to write all these formulas on the blackboard. So this was where we arrived on the last slide. Now it's easy to see if these objects have densities, then we can remove the test function in order to end up with a strong form of the equation. Just a little renaming the variables, and then you can remove the test function, and you end up with this. This was declared the strong form. This was on the first transparency as a strong form of the fragmentation equation.
Excuse me.
Yeah.
Can we recover f from b?
This is a good question. F from B, I would say not in general. No. This is a very good question. Yeah. There are only particular results. If some additional properties hold, then, but in general not.
So
There are just a moment. There are even examples where you have two different F and the same B. Yeah.
the mathematical or the physically correct way to state the problem is in the weak formulation at least.
Not necessarily. Why? Well, it depends on what you call physical. I mean, I will come now to the probabilistic interpretations of the objects which remain in the strong form. So it depends on what you are given from the physics. If you are given this complicated object, F, you can start with the weak form. If you are only given some averages, which will turn out the B are just some averages taken from the F, then you can work with this other stuff. So there's no, I would not say that from a physical point of view. For me, from a mathematical point of view, the weak equation is always more convenient to work with. But this is because I come from probability. For analysts, the strong form is more convenient. So again, remember the star property. The star property is just what is on the right-hand side. Just a repetition of. Now the left-hand side has, of course, a probabilistic meaning. The F is a probabilistic kernel, so the left-hand side just means that the expectation of this functional on the cloud of fragments is expressed via the measure B capital. So in particular, if you plug in as a test function the indicator of a certain interval, then the left-hand side tells you that, okay, we are now having the average number of fragments with size in the interval coming up from a splitting of a particle of size x. And the formula tells you that this average number of fragments is nothing else, just the value of the measure B on this interval. Or the function small b, which appears in the strong form of the equation, is just the density of the average number of fragments with respect to the second variable. So this is the interpretation of the objects which occur in the strong form via the object which occurs in the weak form. So a second comment related to this probabilistic representation is that we assumed, so to say, mass conservation with probability 1. This was our assumption. Of course, this implies that there is mass conservation on average, which means taking the expectation of the sum of all these fragments, you get the x. This is the left-hand side here. Now we look what gives us the formula star. The formula star expresses this expectation, which is just the x, via these b and b capital and small b. So it ends up that mass conservation on average is represented via this function b from the strong form in this formula. And you will find, of course, this formula in papers dealing with the strong fragmentation equation as the mass conservation property. So now I'm finishing the introduction, coming back to the strong fragmentation equation. It's just the same which appeared many times before. But now, so to say, we know, or I can explain every ingredient of this fragmentation equation. So C is the number density of particles of size x, meaning if you integrate over a little interval, you just get, so to say, the average number of particles in your system at time t which have a size inside the interval. The A is the rate at which particles of size x break. So this is A here and the A here. And the B, and for this we have worked a little bit. The B is the density of the average number of fragments of size y which come out of a splitting of a particle of size x. And in addition, this integral equality means mass conservation. So this is the fragmentation equation, and now in the second part I will study or discuss some more specific properties of the fragmentation equation. So here's the equation again. This was the mass conservation property. Now look at the right hand side. We have this integral here, multiply it by x, integrate over the whole size space. All functionals are positive, so you can exchange the order of integration. Once you have done this, you end up with this here, and now you can apply this mass conservation property. So the x here and the x here and the dx and the integral just go away and give the y. You end up with this expression. And you see, if you integrate the rest, here the other, the minus term, again also multiply by the x, integrate, you get the same. So one would guess, okay, multiplying the left-hand side, integrating, you get 0, which means mass conservation. And usually, in many cases, this is true, but not always. So the funny thing consists in the fact that for appropriate functions a and b, there are solutions which lose mass, which are not mass conserving. So there's the arrow and the derivation. You have subtracted infinity from infinity. So, and this strange behavior of the solutions of the fragmentation equation under some conditions has been first observed in a mathematical paper by Filipov and later rediscovered in the physical context by McGrady and Ziff. The first one called it the formation of dust, and the second called this a shattering phenomenon. So now I give a condition which is a little bit more precise. Under some regularity conditions on B, which I will not specify in this talk, you have a non-conservative solution if and only if this function A, which was the fragmentation intensity, so how fast the fragmentation process goes on, if this function grows sufficiently fast at zero. And sufficiently fast means that this integral should become finite. This is a very...
So, sorry, that's always infinite time, formation of dust infinite time.
Yeah, yeah. And the funny thing with the dust is even, it starts at any positive time to lose. So because it's a linear equation. In the nonlinear, you have this gelation stuff which starts only at a fixed time. Yeah? But here it immediately goes down. If it goes down, then it goes from the beginning. So according to this criterion, you can of course derive sufficient conditions for shattering. In particular, this any inverse power law growth is sufficient for the shattering, and even a little bit less. So what I want to do next is to characterize this phase transition or this strange behavior in terms of stochastic models. What happens inside the stochastic model if this happens to the equation? This was simply a property of the equation. And to do this, we have again to prepare a little bit. So I will spend a couple of minutes on explaining how the so-called minimal jump process is defined. So consider a rather general space here. We need a rather general space because we want to handle later this direct simulation fragmentation model, which just was described as any finite collection of delta measures. So we need some kind of generality here. So let's Y be such a space, locally compact subgravimetric, and Q be a kernel on Y. Kernel means it must be measurable with respect to the first variable and must be measured with respect to the second variable. So then the time evolution of the process, of the jump process, is defined in an easy way. So given a state Y, the system or the process waits an exponentially distributed time given by this parameter. This is the parameter of the exponential distribution. And then it jumps to a new state according to the distribution given by the kernel. So obviously the jump times provide an increasing sequence, and it can happen that this limit of the jump times is either infinity or it's finite. This will depend on the kernel. So in general, one can define the so-called explosion time just at the limit of this increasing sequence of jump times. And then this so-called minimal jump process is defined on the one-point compactification. So just a single point is added to the state space Y, And the process is defined in the usual way. I mean, this is a Markov chain which comes up from all the jumps up to the explosion time, and after the explosion time, just a new state which we have gained here. So to say, the process stays in this infinity or zero or whatever your compactification point is. Yeah, so it's a very simple object. So it lives on rather general spaces. So and by definition, this minimal process is called regular if the explosion time is infinity with probability 1, and otherwise it's called explosive. And here is a criterion, a general criterion, telling us when this minimal jump process is regular. Namely, it's regular if and only if this series C here diverges. So the yk is just the Markov chain of the different positions the process has after each of the jumps, and the lambda is the parameter of the waiting time. Okay, this is necessary and sufficient, therefore it's not very explicit. But what one can see from this condition is that if the waiting time parameter is bounded, then we get regularity, no explosion. If we would expect explosion, this means that lambda must be unbounded and the Markov chain must reach the infinity with an appropriate speed. So here's the first theorem, which makes a connection between a condition which was sufficient for shattering in the equation and the property of the stochastic model. Namely, the theorem tells us if this fragmentation rate grows sufficiently fast at 0, then the direct simulation process explodes almost surely for any initial distribution. So I just recall what was the definition of the direct simulation process. It was given on Z state space, and this together with this was a transition kernel. So it's another point why this description in terms of empirical measures instead of systems of particles is slightly more convenient. So basically I'm ready with the main message of the talk, but since there is enough time, I will consider a second stochastic model and study again its connection with this shattering phenomenon in the fragmentation case. So the second stochastic model is much simpler than the first one, so it is less intuitive. Okay, let's start from the beginning, and later we will see what comes out. So for this second model, again, I start with a certain equation, which is, from the notational point of view, is exactly the same as the strong form of the fragmentation equation, except that here now we assume that the B, and therefore I introduce the tilde, the B is now a probability density with respect to the second argument. I will discuss, so to say, the explanation of all this stuff will come on the next two on the next two slides. Now, this is a strong form. Again, the C tilde is a number density, but a trivial one in this case. The weak form, because there will be only one particle, the weak form is obtained from here by multiplying with the test function integrating, and you see the right hand side is now very easy. First it's linear, I mean this is linear, there's only one particle involved, but the most important difference to the first stochastic model is that the jump is very easy. So now the x simply jumps to a smaller y. Okay. So in this case, we don't have a particle system, we just have one particle. And this particle makes random jumps to lower states, coming closer and closer to zero. Now, the random mechanism of these jumps is given by these functions a and b tilde. Now the connection between the particle, it's now not a system, between the particle and the equation is again the direct consequence of the Kolmogorov's forward equation. In this case, even the generator is much simpler because everything lives on the one-dimensional state space of a single particle. So now I want to make the connection, one has to go step by step, a connection of this second model with the original fragmentation equation. And the connection is very simple. So if we have a solution of the new equation, then this transformed object satisfies another equation, which is just the original strong form of the fragmentation equation. This is easy to see. Just divide by the x. Divide by the x here, you get this. You have divide by the x and multiply. So you get this, provided you define the b here in the correct way. Note that the b, which occurs now in the standard equation, so to say, satisfies the mass conservation property. It's simply a consequence of the fact that the b tilde was supposed to be a probability density. So the most important thing now is to make the connection with the direct simulation process. And here again, so it was already interesting in some sense because we have a much simpler stochastic model, the second one, which provides us an equation which is in some sense equivalent to the original equation. So this was already some message that the original equation in fact can be modeled by a much simpler stochastic model than the original splitting one, which was very complicated. But this connection is even more interesting between the second model and the first model. Again, we have to go back to our property star. And when you think a little bit, you see that this B capital, which was the average number, measuring the average number of fragments, can be represented as a mixture of the sum of the delta functions. Yeah. And having this representation, you can represent the new, so to say, the transition kernel of the second stochastic model via the original fragmentation kernel. And this gives you a probabilistic interpretation of the second model in terms of the first model, which means instead of each time splitting your particle x into many pieces and then going ahead and your system goes, and the number of particles in your system grows very fast, you just create one cloud of fragments. One cloud of fragments, and then you decide which of the clouds, which of the elements of the cloud you take. This is according to these probabilities. Then you replace your original particle by this cloud. Your process goes down and down and down. So now the statement you want me make me to stop. Actually, I started 15 minutes later, so I planned to talk. I would have skipped the second model if I knew that I don't have time. But I started 15 minutes later.
No, just 7 minutes later.
7 minutes later? Yeah, okay. No,
I rounded off.
Yeah.
There's no pressure.
No, I had the choice to introduce the second model or not, but you know.
It's interesting.
But at the full hour, we should probably, some people, I don't know, need to cut out.
Okay. This is the theorem for the second model. Because I need some time to discuss the references, I will not comment too much on the theorem. Simply the basic message is that under the condition which gives shattering phenomenon in the equation, and under some additional technical condition, the second stochastic model also explodes. Okay. Now I did not mention any references. Now I have a couple of slides with references. Because I touched very many subjects, so I could not go into too much detail. So for people who are interested in stochastic models related to the Boltzmann equation, I recommend the historical chapter of this book, written together with Razanov, who also was here at the beginning of the semester. General interaction, including all these which I presented, are covered. My knowledge comes basically from this joint paper. But there's a recent book by Vasily Kolokoltsev, just appeared in Cambridge University Press. So you can find a lot of stuff related to general interactions there. Now an overview of the fragmentation stuff is given in a recent paper by myself. Now, these are the most interesting references for people. If you want to study something more, this shattering phenomenon, this is the original paper by Filipov. Maybe here are some people who know Russian. So the original term for this shattering was raspylenie. Pyl means dust. So I would translate it by saying dustification, but dustification is not an English term as far as I know. So in the translation, it was later named decomposition or disintegration. And the idea of this stuff goes back to Kolmogorov. This is a paper where the term shattering was coined, so to say. Benedicto Haas has a very nice paper, very precise conditions in the homogeneous case. These are two monographs related to the subject. Bertrand, mainly about stochastic models, Banazia, Carlotti, mainly related to the functional analytical point of view of this stuff. Explosive jump processes. There's a lot of literature on this. In historical account, you can find in Kyla Chang's book. There's a long introduction to the stuff. Etienne Kurtz is this book which I would recommend to everybody who has to work with Markov processes. Wu-Fa Chen has a good exposition of the general state space, minimal process stuff. James Norris has a nice exposition of the discrete case. Explosion criteria, which have been used in the theorem, go back in the one-dimensional case to a paper by Kerstin Klebaner. and in the general case to a paper by myself. And that's it. I will not comment, I leave it to the audience if you want to ask questions. I will come back to some of the questions. Thank you.
Thank you very much. You already had it.